Okay, today we'll be getting a little bit more in depth on the idea of linear momentum, and we'll be going through a practice problem that I drew up. So as you can see here, we have a wishbone looking pipe with fluid coming in at 15 feet per second through this end and coming out at these two ends at a rate of 15 feet per second in V3, which we'll solve for later. As you can see, the areas for each pipe are labeled in the diagram, and we're dealing with water here. Now it's important to set up your axes to get an idea for which is the positive direction. So for this situation, we have x being positive to the right and y being positive going up. So we want to calculate this f of x value, which is the reaction force in the x direction. And to do that, we need to use the idea of linear momentum. So to start off, we're going to calculate this v3 value, which will help us later down the line, as you'll see. So in order to do that, we have to use the concept of rate in equaling the rate out in a steady state situation. So we relate the flow rate to one another. So the flow in has to equal the flow out due to the conservation of mass. So as you will see here, we have our flow in, which is this 15 feet per second times the 1 foot squared, equaling the flow rate out, which is V3 times 1.2 feet squared plus 15 feet per second times this 0.6 feet squared. Doing the calculations, you'll find out that V3 equals 50 feet or 5 feet per second. Okay, so at this point, you're going to want to sum your external forces and set it equal to the net outflow of linear momentum. So as you'll see here, that's the equation. Sigma F is your sum of external forces, and this integral across the controlled surface is essentially the outflow of linear momentum. So that equals out to the mass rate out times the velocity out minus the mass rate in times the velocity in. And for this question in particular, we're trying to calculate f of x, so we have to be wary of directional velocities. As you can see here, this pipe is somewhat at an angle, so it's going to have velocities in both the y and the x. This pipe here is only going to have velocity in the y, so that'll end up canceling out when we calculate f of x, as you'll see later in the problem. So setting this up, sigma fx is going to be equal to your density times area times v2, and this density A2, or this density times area times velocity, is your mass rate term. So let's make note of that. M dot is equal to EBA. And this U2x is the velocity in the x direction for v2. As we'll see, that's 0. For velocity 3, we have this velocity at a 40-degree angle, so we're going to make that 5 times the cosine of 40 degrees. And since our velocity in is strictly horizontal, that would just be 15 feet per second. So as you can see here, we have this equation set up. We have the density times our 0.6 feet squared from A2 times the 15 feet per second, which is the velocity of V2, times this 0 value, which is the velocity in the x direction for this part of the pipe, since it's strictly vertical. For this third section here, we have an area of 1.2, overall velocity of 5, and then this horizontal velocity of 5 times the cosine of 40. Pipe 1, we have area 1 of 1 foot squared times overall velocity of 15 feet per second times a x direction velocity of 15 feet per second. So that means our sum of external forces ends up equaling negative 391.916 pounds. And now what we have to do is we have to set this value equal to the sum of external forces from our diagram here. So the way we do that is we want to calculate the pressure forces and the reaction forces and set it equal to this negative 391.916. So going back to our diagram, it's stated that we have pressure at this first section of the diagram of 15 pounds per square inch. And the pressure at these two ends of the pipe are going to end up being 0 due to the idea of a free jet. So our equation ends up simpling down to P1A1 minus F of x, equaling this negative 391.916. So plugging in the numbers for that, we have negative 391.916 equaling 15 pounds per square inch. Converting that into pounds per square foot by multiplying by 144, carrying that over and solving for f of x, we get 2,552 pounds. So there you have it. That's linear momentum. Thanks.